Okay, so welcome to the next installment in this series of screencast videos on our review material from Chapter 1. This is a continuation of Section 1.2 on the properties of the real number system, and in this video we're going to focus in particular on the arithmetic of fractions. Now, most of the time when we're working in Math 1410, when we're dealing with real numbers, we won't have to worry too much about irrational numbers. Most of the time we're going to be dealing with rational numbers. So remember that rational numbers are numbers which are in particular real numbers, but they're real numbers that can be written in this form here. P over Q, where P and Q are both integers, and Q is not equal to 0. So the rational numbers are simply your fractions. And fractions are going to come up quite a bit in this course, especially once we get into things like solving systems of equations. You're going to find that it's frequently the case that you have to divide by some integer, and suddenly you end up with fractions all over the place. And if you're not comfortable working with fractions, you're going to find that it is a bit of a struggle to get through some of the computational stuff in this course. So, even if you feel like this is junior high material, you learned it a long time ago, there's a good chance you're a little bit rusty, and it doesn't hurt to review some of this material. Some of you may have found that you had trouble with fractions all along, and if you're in that boat, don't worry, because a lot of people are. Now, in this set, there's a fair amount of redundancy, right? For every choice of P and Q that I can make, I don't necessarily get a completely new fraction. There are a lot of different fractions that could, in fact, be equal. The way we define equality of fractions, we say that, well, a fraction A over B is equal to a fraction C over D, provided that A times D is equal to B times C. So there's sort of this cross multiplication that you can do to check whether or not two fractions are equal. And this definition of equality leads to the idea of equivalent fractions, that there are lots of different ways that you can write down the same real number, because if I take a fraction A over B, I can actually multiply top and bottom, as long as whatever I do to the top I also do to the bottom. Multiplying top and bottom by this same number doesn't actually change the value of the numbers. So A over B is the same thing as Ka over Kb for any integer k, as long as that integer is not equal to 0, because of course 0 over 0 is not defined. And you can see that this has to be true, because if I multiply A times Kb, well, we know that order of multiplication doesn't matter, so I can write that as Kab. On the other hand, B times Ka, well, again, I can write that as Kab. So these guys are equal. They satisfy this definition of equality of fractions, and so any two fractions of this form are going to represent the same real number. So for example, we know that 1/2 is the same thing as 2/4 is the same thing as 3 over 6, and so on. So there are many ways of representing the same real number as a fraction. Now, how do you add or subtract fractions? Well, when you're dealing with the sum of fractions, so you want to do something like A over B plus C over D, you might remember that there's a rule. You have to get a so-called common denominator. So the trick here is you use this idea of equivalent fractions to say, well, I can take A over B and I can multiply top and bottom by D. I can put a D in there. And similarly, I can take C over D, and I can multiply top and bottom by B. Right? As long as, well, B and D are non-zero, but they'd better be non-zero or the fractions I started with aren't defined in the first place. And now, of course, D times B is the same thing as B times D, and I can write this as a single fraction. I can say, all right, so this is the same thing as AD plus BC, all divided by B times D. So this is the rule for addition. Now, if you've never seen really an explanation for this rule, it doesn't hurt to kind of go over it. So let's pick a couple of fractions. say 2 over 7. Now, one way to understand a fraction is as follows. Take a copy of the unit interval, all the real numbers from 0 to 1, and you divide that thing up into 7 equal pieces. 1, 2, 3, 4, 5, 6, 7. So the denominator tells you how many pieces you should divide this interval into. We've got a 7 here, so we take 7 equal pieces. The numerator, the 2 up top, tells you how many of those pieces you should take. I should take 2 of them. So that chunk of the number line there, the length of that piece of the number line, gives us a visual representation of the fraction 2 over 7. Similarly, I could take, let's say, 3 over 5. So I take the same unit interval, I'll try to write it as the same length, 0, 1, and I divide it up into 5 pieces of equal length, and because I've got a 5 in the denominator. In the numerator, I've got a 3, tells me I should take 3 of those pieces. And so now I've represented those two fractions. But if I want to add them together, you run into a bit of a problem, because in some sense you're comparing apples and oranges. You're taking 2 of a segment of the interval of one length, and you're adding 3 times a segment of a different length. And so it would be much easier if you were combining things that were of equal length, and then you could simply say how many of them you had. And so the way you do this, kind of the thinking behind it, is, well, if I take each of these pieces of length 7 and further subdivide those into 5 equal pieces, then I will have a total of 35 equal pieces over the entire interval. And similarly, if I take each of these 5 pieces, representing the fraction 3 over 5, and I divide each of those into 7 equal pieces, again, I'm going to have divided the interval up into 35 equal pieces. And so that's what you're doing when you're adding two fractions, is you're doing this sort of subdivision trick, which allows you to say, well, 2 over 7 plus 3 over 5, so you say, okay, so for 2 over 7, I multiply top and bottom by 5. 2 times 5 is 10. 7 times 5 is 35. Gives me the 35, telling me that overall I'm dealing with 35 equal pieces. And 3 over 5, I multiply top and bottom by 7. 3 times 7 gives me 21. 5 times 7 gives me 35. And now that the denominators match, that tells me that I'm adding things that are the same size, and it kind of conceptually makes more sense to add them together. And so I get 31 of them in total. So I get 31 over 35 as the sum for my two fractions. Subtraction is similar. The only difference with subtraction is that you change the addition to a subtraction, right? The sign changes. We know that subtraction is the same thing as adding the negative. And so if you go through the same steps, you'll find that the difference between the two fractions is AD minus BC over the same common denominator. So if we work with our same numbers from above, 2 over 7 minus 3 over 5, I'm going to get 10 minus 21 over 35, so I get minus 11 over 35 for the difference. One thing to keep in mind, you may have been told at some point that it's necessary to always find a lowest common denominator. This isn't actually the case. In many cases you will end up with the lowest common denominator, but it's fine if you don't get the exact lowest common denominator. That just means you're going to end up at the end with an equivalent fraction where you can, if you want, do some simplification. The only advantage of using the lowest common denominator is that it'll keep your numbers a little bit smaller, and that might make the arithmetic easier if you're not using a calculator. Alright, now we come to multiplication and division. And the rule for multiplication is a bit more straightforward. If I want to take a fraction a over b, multiply by a fraction c over d, I simply multiply the numerators and I multiply the denominators. You just multiply across. Top times top, bottom times bottom. Notice that although addition requires a common denominator, The same is not true for multiplication. There's no common denominator involved here. You simply multiply the tops and you multiply the bottoms. And maybe one way to sort of think about why this should work is to remember that when we define division by b, we define division as multiplication by the reciprocal. So the fraction a over b, you can think of it as representing, well, multiplication by a followed by division by b, or whichever order you prefer. And so if you think about, multiplying a fraction by an integer, if I take 2 times c over d, well, that would be, like adding it to itself, c over d plus c over d. And d is the denominator in both cases, so you would get c plus c up top, gives you 2 times c, right? So it makes sense. If b is equal to 1, it makes sense. If you're just multiplying a fraction by an integer, that you should multiply the numerator by the corresponding integer. The denominator you can think of as dividing, and you can kind of play around and you can reason it out and you can say, okay, that makes sense as well. If I want to multiply by a over b, dividing by b, I need to multiply by b in the denominator. Right? Multiplying in the denominator makes the denominator bigger. That makes the overall number smaller. Okay. So as a quick example, if I wanted to do let's say I wanted to do 2/3 times 7 ninths. I simply do 2 times 7 gives me 14. 3 times 9 gives me 27, and I leave it at that. Let's do one more. If I want to do, let's say I want to do 3/4 times 2 ninths. Now, this is a case where you can just go ahead and do it the same as before. You can say 3 times 2 is 6. You can say 4 times 9 is 36. But now, of course, the fraction that you get here, it's not reduced. You can, if you want, you can say, well, this is 6 times 1 over 6 times 6. And then you can cancel these 6's and simply write it as 1 over 6. Now, when that happens, that tells you that you could have done some simplifying ahead of time. When you're multiplying, one of the things you could do is you could say right away, well, this 4 is a 2 times 2, right? This is 2 times 2. This 9 is 3 times 3, and you're multiplying the tops and the bottoms together, and so you can scramble these around, right? You could put the 3 on the right, you could move the 2 to the left, and you can say, well, you know what, this 3 is going to cancel with that 9 and leave me with a 3 here and a 1 here. The 2 is going to cancel with the 4, leave me with a 1 here and a 2 here. And then you simply have 1 times 1 divided by 2 times 3, you get your 1 over 6 right away. So when you're multiplying, it's often useful to look for cancellations right away because it's going to simplify your arithmetic. Now, what about division? Well, we use the same rule that we came up with on the last video when we defined multiplicative inverses. We said, well, the way you define division is as multiplication by the inverse, multiplication by the reciprocal, right? And so you can see that the inverse of a over b, the reciprocal of a over b, it must be b over a, since if I do a over b and I multiply by b over a, I get ab over ab, which is 1. And so that means that if I want to do division, if I want to do, say, a over b and divide by, let's say, c over d, well, division is the same thing as multiplying by the reciprocal, so this is a over b times d over c. So we turn division into multiplication, and then it proceeds as above. We do a times d, and we divide by b times c. Okay. Continuing along. We want to make a few more remarks on this issue of reduction, cancellation, coming from this idea of equivalent fractions. So what you want to keep in mind here is you have to be very careful. There's a tendency to want to cancel things that you're not allowed to cancel, right? So if I was doing something like, 4 plus 6 over 8, right? Well, I know that I could. There's a couple ways of thinking about this. I can say, well, that's 10. That's 10 over 8, and I know that 10 is 2 times 5. I know that 8 is 2 times 4, so I can cancel the 2's, and I get 5 over 4. Or I guess you could think of it initially, well, there was a common factor. I could have written this as, I could factor it at 2. This is 2 times 2 plus 3, using the distributive property, and then cancel the 2's right away. But we can cancel in a situation like this, right? But there's a tendency to want to cancel things that you're not allowed to cancel, like to cancel. So some people might say, oh, no, 4 over 8 is a 1/2, so I'm gonna cancel that 4 and leave a 1, and I'm gonna cancel the 8 and I'm gonna leave a 2. But that's simply not valid, right? I can't do that. I can't say that. I couldn't say that this would be 1 plus 6 over 2. That gives me 7 over 2. That's certainly not the same thing as 5 over 4. So we know that's definitely not something which is valid. But nonetheless, there is a tendency, if we get to algebraic expressions, something like x plus 1 over x squared, there's always a good subset of the class that says, hey, let's cancel those x's. In this case, those x's don't cancel. There's nothing you can do. There is no simplifying here that you can do. You might want there to be some simplification, but there simply isn't a simplification that you can do here, because there's an x here and there's an x here, but there is no x in this term, right? Unless that x is a common factor all the way across the numerator, there's nothing I can do. So I can't do anything to simplify that. I can't pull out the x. On the other hand, if I had something like, let's say I had x squared plus x over x squared, something like this. Oh, now I can simplify, because there's an x which is common to the both. So if I use the distributive property, right, I can factor out an x. X squared plus x is the same as x times x plus 1. X squared is x times x. And now you can use equivalent fractions to say, look, I've got an x here, I've got an x here, those are common factors, they cancel, and I simplify this down to x plus 1 over x. So I can leave it like that. Now, if you did, I guess there is a bit of simplification that you could do here, and you could have done it up here. It's not quite true that there's no simplification. If you think of this x as the common denominator, you could reverse the addition process, right? You could say, well, x plus 1 over x, that's the same as x over x plus 1 over x. And x over x is just 1. So this is 1 plus 1 over x. You could write it like that if you want. But it's worth kind of spending some time playing around with fraction arithmetic if you're a bit rusty. Work on it, get comfortable with working with actual numbers and realizing how the arithmetic works. And once you kind of get a handle on that, it should help you avoid some of the mistakes that you might run into when you're actually doing the algebra, once you have some variables involved. Okay, so that's it for this video. I think we'll stop it here, and we'll continue on the next one with Chapter 2 and complex numbers.